Hello again, students. In our previous video, we discussed how the Schrödinger equation led to the ability to graph three-dimensional regions of space which define the probability distribution for an electron. And we call those regions of space orbitals. And we saw how taking the square of the wave function led to these different orbital types. There are s orbitals, which are spherical, p orbitals, which are dumbbell-shaped, d orbitals, and f orbitals, which are of more complex shape. I'd like to point out something else that's important here, and that is that for every given energy level, for example, if it's n equals 1 or n equals 2 or n equals 3, you will only have one of these s orbitals in that energy level. You may have p orbitals in the energy level, and if you do, you'll have 3 of them. You may have d orbitals in the energy level, and if you do, you will have 5 of them. And you may have f orbitals in that energy level, and if you do, you will have 7 of them. Well, I've just given you several numbers that are related to these orbitals. I've given you their spectral designators, s, p, d, and f. I've told you their shapes. Well, there's a mathematical way to represent the information that I've just given you using numbers that reflect each of those properties. And those numbers are called quantum numbers. So that leads us into the topic for this video. So on the next page, to simplify discussion of specific electrons, we want to talk about which electrons specifically in a particular orbital. And in order to do that, we need to describe them, the electrons, using a 4-number address code. And these 4 numbers are called quantum numbers. So quantum numbers. And they denote certain important characteristics of the electron. For example, the energy level in which we find the electron, or the orbital type and shape that we find it in. Those are characteristics, and we're going to describe those characteristics by referring to quantum numbers. So for each unique set of 4 quantum numbers, there's only 1 electron. So a set of quantum numbers will specify a unique electron. So the first 3 quantum numbers that we're going to talk about, they are symbolized with a lowercase n, a lowercase l, and a lowercase m with a subscript of a lowercase l. So it's n, l, and m sub l. Those first 3 quantum numbers are going to describe the unique orbital in which we find the electron. And once we have identified the unique orbital that we're talking about with those 3 quantum numbers, then the 4th quantum number that we're going to use is lowercase m with a subscript of a lowercase s. So it's m sub s. And that 4th quantum number, m sub s, will describe what's called the spin of the electron within that orbital. So that 4th quantum number will help us determine which electron we're talking about in that orbital. So just to rewrite these, it's n, l, m sub l, and m sub s. And that is an L, not a 1 or an I, okay? Those are the 4 symbols for the 4 quantum numbers. Now I'm going to go through each one of these in turn and tell you what they represent and what their possible values can be. So the first one is called the principal quantum number, and it is the letter N. And we have seen that one before, back when we were talking about the Bohr model of the hydrogen atom and how electrons could be promoted to energy levels and then relax back down to energy levels. And we said they could be in the n equals 1 or n equals 2 and so forth energy level. That we've already seen this quantum number. So this n quantum number specifies the energy level. And the higher this number, the higher the energy level. And we've seen that again. We've seen how an electron can be promoted up to an n equals 4 and then cascade or relax back down to a lower n value, a lower energy level. Another way that we often refer to this n value, or this principal quantum number, or this energy level, is by referring to the shell. The shell in which the orbitals can be found. And you can imagine the atom having a shell and another shell and another shell, so larger and larger and larger shells around it, larger and larger and larger energy levels, so as the principal quantum number increases. So that's what it is, what it represents, and the values that it can take, it must be a positive integer. So what does that mean? So it's the possible values, therefore, are 1, 2, 3, 4, and all the way up, theoretically, to infinity, okay? And note that the lowest possible value for n is 1. We never have an n value that is 0 or a negative number. Well, one of the consequences of the n value being the energy level is that as we go higher and higher in n value, the orbital size increases. So the n value is roughly relative to the size of the orbital, because it describes the relative distance from the nucleus where the electron density is distributed. So you can think of an n equals 1 s orbital, a sphere, being a small sphere. But an n equals 2 sphere being a larger sphere. So we would say this is a n equals 1 s orbital, and this is a 2s orbital. And what that means is that this first number is the n value, and the letter tells us what shape the orbital is. And just to remind you that you have seen the n quantum number before, because when we were doing calculations of energy absorbed or emitted by an electron when it transitions between its energy levels, we use the n values, the n final and n initial levels. So we've seen that one before. So there again, it can be a positive integer. It is also called the shell, and it is related to the size of the orbitals. And the larger the n value, the larger the size of the orbitals. Moving on to the second quantum number, we call it the secondary quantum number, and it's also called the angular momentum or azimuthal quantum number. That's a typo. That little parenthesis there is a typo. The angular momentum quantum number or azimuthal quantum number, you might see those terms in your readings about this. And it is lowercase l. That is the second or secondary quantum number. And it indicates the shape. So the n quantum number is relative to the size. The L quantum number tells us about the shape. So remember, these quantum numbers are all about the characteristics of the orbitals and the electrons in the orbitals. So the n value tells us the size, the L value tells us its shape. So the L value indicates the shape of the orbital. Or another way of saying that is the contour of space, or the region of space in which the electron's density, or another way of saying that is the electron's probability distribution, will be. And this is also called the subshell. So the n value is the shell, the L value is the subshell. The L value can take on certain values, and it must be an integer from 0, starting from 0, through all positive integers up to n minus 1. That means 1 less than whatever the n value was. Okay? So the number of possible L values equals the value of n. What does that mean? If n equals 3, if we tell you that n equals 3, the principal quantum number is 3, what are all of the possible values of L? Well, consider what the rule is. It's all integers, any integers, starting with 0, going through positive integers up to and including n minus 1, but it cannot go up to the n value. So take a moment and write down what you think all of the possible values of L are going to be given that rule if we stipulate that the n quantum number equals 3. Take a moment and do that. Okay, I hope that you can see that we're going to include 0 as one of the possible values, because the rule says it's an integer from 0. So what is the n value? It's 3. So we're going to start at 0 and go up to 2. So 0 is a possible L value, 1 is a possible L value, and 2 is a possible L value. Would we go up to 3? No, because the L value cannot go up to n, it has to stop at n minus 1. So when we say the number of possible L values, it equals whatever the value of n is. So if n equals 3, there are 1, 2, 3 values for L. And why is that? Because we start at 0 and go up to n minus 1. So we're going to have the same number of L values as whatever the value for n is. Okay? Now, pretty soon, you're going to start getting a little bit of information overload, and we're going to power through it a little bit, and then we're going to come back to help resolve some of that. But one of the things that helps us deal with these numbers is that rather than using numbers to represent L values, we usually use what's called their spectral designators. And the spectral designators, you don't need to know that term, but if the value for L is 0, then we use an S. If the value for L is 1, then we use the letter P. If the value for L is 2, then we use the letter D. And if the value for L is 3, we use the letter F. And you have seen those letters before. So let's imagine what this means. If the value for L is 0, then that's an s orbital. If the value for L is 1, then it's a p orbital. These are orbitals, right? These are the shapes of orbitals. The orbitals and their shapes. So very often you will see orbitals referred to in this manner. There will be a number and a letter. The 1s orbital, the 2s orbital, the 2p orbital, for example. And what that means is if you have the 2p orbital, it means that the n value is 2, so it's the second energy level, and the L value equals 1. And that means that it is a dumbbell shaped. Orbital, if the L value is 1. That letter P is the L value equaling 1, S, P, D, and F, right? So if you see an orbital referred to by a number letter designator, then you're being told the N value, that is the energy level, and you're being told the L value, which is corresponding to a shape. So a 2p orbital is in the second energy level, and it's a dumbbell-shaped orbital. Moving along, we're going to talk about the third quantum number. And the third quantum number, remember we have n, L, and the third number is m sub L, and that's a lowercase l subscript. And this third quantum number, m sub L, the magnetic quantum number, indicates the orientation in space, which is to say which way the orbital is pointing, how the orbital is aligned in space. So for example, if I have a dumbbell, I could have it aligned along the x-axis, or I could have it aligned along the y-axis, or I could have it aligned along the z-axis. Those are three different orientations for a p orbital. And that is why we have, if we go back to our diagram, that is why we have three different p orbitals. We have a px, a pz, and a py, because one of these p orbitals is aligned along the x-axis, one is aligned along the z-axis, and one is aligned along the y-axis. What tells us which direction the orbital is aligned in? It's going to be this third quantum number, the m sub L quantum number. Now here's where the rules start to get a little bit different for what these values can be. The m sub L quantum number must be an integer again, but it now takes possible values from negative L, whatever the L value is, out to the negative value of L, through all integers on the number line, through 0 and including 0, through all positive integers up to the L value. So this magnetic quantum number, m sub L, depends on whatever the value of the azimuthal quantum number is, which is the L quantum number, right? So here's another sample problem for you to do. Given this rule that the m sub L values can take values from negative L through all integers up to and including 0, and then through all positive integers up to the L value. With that in mind, here's a sample problem I want you to do. If the L value equals 1, then what are the possible values of m sub L? So I'd like for you to take a moment and write out all the possible values of m sub L. So go ahead and pause the video for a moment and answer that, and then resume the video when you're done. All right, let's take a moment and answer this. If L value equals 1 and m sub L can be down to the negative L value, then we know that the possible values for m sub L are going to start with negative 1. Then they go through all integers through and including 0. Well, there are no integers between negative 1 and 0, so we'll just go to 0. And then through all positive integers up to and including the positive value for L. Well, there are no positive integers between 0 and the L value, so we'll just say a positive 1. I could have left off the positive sign, but I just want to emphasize that we have a negative L value of a negative 1, 0, and a positive 1, and those are the possible values of m sub L if the L value is 1. If the L value were 3, then what would be the possible values of m sub L? It could be negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3. That's if the L value were 3. All right, and note that the number of possible m sub L values, 1, 2, 3 in this case, equals the number of orbitals for that given L value. Well, what does that mean? If the L value equals 1, what kind of orbital is that? What shape of orbital is that? That is the p orbital. If the L value is 1, it's a p orbital. If it's a p orbital, how many p orbitals are there in that shell? There are 3 of them. 1, 2, 3. So there's a px, py, and pz. Okay. So the number of the possible m sub L values, how many possible values you get, tells us the number of orbitals that are going to be in that L value subshell. All right, moving on. These first 3 quantum numbers, n, L, and m sub L, have told us the energy level of the orbital, they've told us the shape of the orbitals, and they've told us the orientation of the orbitals. So basically, they have defined a specific orbital within a specific energy level. The 4th quantum number is going to tell us which electron that we're talking about within that orbital, because you can have more than 1 electron in each orbital. You may recall that you can have 2 electrons in each orbital. So it's this 4th quantum number that's going to tell us which electron of those 2 we're talking about. Another way of thinking about it is that the first 3 quantum numbers tells us which house we're talking about, and the 4th quantum number tells us which person within that house. So we've got basically an address and an identifier of a specific electron. And this lets us talk about specific electrons in specific orbitals. So this fourth quantum number is called the electron spin quantum number, and its symbol is m sub s, lowercase m with a subscript of s. And this indicates the spin of the electron within that orbital. And by convention, it is either up or down. So it is either an up, and notice I'm using a little fishhook type of an arrow. It doesn't have, it's only a half of an arrowhead. So that's an up spin or a down spin. All right, and that's the convention for showing an up spin or a down spin. Now the numerical equivalents of those are a plus 1/2 or a minus 1/2. So a positive 1/2 or a minus 1/2 are the possible values for the m sub s quantum number. These values do not depend on the previous quantum numbers. So it doesn't matter which value n has, or L has, or m sub L has. There are only two possible values for m sub s, and it could be either one of these. An up spin, which is plus 1/2, or a down spin, which is minus 1/2. And therefore, again, there are two of these electrons in each orbital. So they have opposite spins, up spin and down spin. I'll just take a quick moment to reflect on this notion of a spin state. Electrons are not really particles that spin. So why do we call them spin states? Well, electrons do behave electromagnetically as if they were charged particles that were spinning. And as a result, this spin state reflects that characteristic. But remember, electrons aren't really particles. They're wave functions. And so we use this word spin to refer to a quantum property of electron wave functions. And for our purposes, we can just treat them as if they have an upspin or a downspin. All right, now that I've gone over the four quantum numbers, n, L, m sub L, and m sub s, what they represent, and what their possible values can be, I would like for you to do the following. I have a chart here, and I would like for you to fill in that chart, and then I would like for you to try to answer the sample problems A, B, C, D, E, and F. So it's a fair bit of work for you to do, and when you're done with it, you can resume the video and I'll work through this with you. I suspect that you will find some of these relatively easy to answer, and some of them, maybe the last few of them especially, you might find particularly challenging. But that's okay. They're intended to make you think really hard about what these numbers are representing. So as you are working through this chart, I will do the first row for you so that you get an idea of what we're looking for. So the first quantum number is n, and its name is the principal quantum number. And its possible values are positive integers. And that is 1, 2, 3, 4, and so forth, up to infinity. And it describes the energy level, of the orbital. It also describes the size of the orbital. And it also describes the distance from the nucleus. Okay, so there's a model for how I want you to fill in the rest of this chart. And when you've done that, I want you to go on and do the sample problems. So pause the video now if you would please, and go ahead and do all of that. And when you're done, you can resume the video and I will fill this in. Okay, resuming the video, we're going to fill in the rest of this chart. We have the quantum numbers n, L, m sub L, and m sub s. The name of the second quantum number is called the secondary quantum number. And the possible values for L, it must be an integer, and it starts at 0, and it goes up through all positive integers up to 1 less than the n value, whatever the n value is. So L can never equal n. And it describes the shape of the orbital. So the n value describes the size of the orbital, and the L value describes its shape. Moving on, the m sub L is the magnetic quantum number. Possible values include integers, beginning at a negative L value, whatever the L value is that we've chosen, up through integers through 0 and including 0, up through integers up to and including the positive L value. And this describes the orientation in space of the orbital. Basically the alignment or which direction the orbital is pointing in space. And then that brings us to the fourth quantum number, m sub s, and this is the spin quantum number. And there are only two possible values for the spin quantum number. It must be plus 1/2 or minus 1/2. And again, these numbers do not depend on the previous three quantum numbers. As long as the m sub s spin quantum number is one of these two values, plus 1/2 or minus 1/2, then they are valid. And this describes the spin of the electron in the orbital. Okay, so now that we've filled in this chart, we're going to continue on and answer these questions. What are all the possible L values for an orbital with the n value equals 4? And we know that if n equals 4, then L values start at 0, go through all integers up to 1 minus the n value. If n is 4, then n minus 1 is 3, so the L values will be 0 up to 3. So L could equal 0, 1, 2, and 3. Sample problem B, what are the possible m sub L values for an orbital if it has an L value of 2? So if the L value is 2, we can see that the rule for the possible values for m sub L are negative L through all integers, including 0, up to a positive L value. So if L is 2, then we go down to -2, -1, 0, plus 1, plus 2. So m sub L, possible values are to the negative L value, which is -2, -1, up through and including 0, then +1 and +2, like so. Continuing on the next page. Sample problem C. Which of the following is a valid set of quantum numbers for an electron? So here we have 4 possible sets of quantum numbers. The n, L, m sub L, and m sub s values are provided. So we've got to look at these values and see if we are following the rules for their possible values. So let's take each one in turn. We'll start with set A. Is set A a valid set? Well, let's look at the n value. Can n equal 2? Yes, n could be all positive integers, so that is a valid n value. If n is 2, can L equal 2? And we know that's not valid because L can never equal n. L starts at 0 as possible values and goes up to n minus 1, so it can never equal 2 in this case. So right there we have an invalid L value, and that means that that is not a valid set of quantum numbers. So moving on to set B. Is it possible to have an n value of 1/2? And right away, we don't need to check anything else. We know that's an impossible n value because n values can only be positive integers. So it cannot be 1/2. So that's an invalid set because of the n value. Set C. Is it possible to have an n value of 1? Yes, that's a possible n value. If n is 1, is it possible for L to equal 0? Yes, because the possible L values start at 0 and they go up to n minus 1. n minus 1 in this case is 0, so L equals 0 is a valid L value if n equals 1. So far so good. Is it possible for m sub L to equal a minus 1? And right there we find a problem. If L is 0, remember that the possible values for m sub L are that they can only go down to a negative L and up to a positive L. So since L is 0, the only possible value for m sub L would also be 0. So we know that that is an invalid m sub L number, and therefore that's an invalid set of quantum numbers. Well, it's not looking good for valid sets so far. All of these are invalid so far. Let's check set D. Is n equals 2 a possible n value? Yes, that works. If n equals 2, can L equal 1? Yes, because the possible L values would be 0 and 1 when n equals 2. If L equals 1, is m sub L equal minus 1? Is that a possible m sub L value? And yes, it is, because if L is 1, then m sub L values can be negative 1, 0, and plus 1. So that's okay. Is it possible to have an m sub S value of a minus 1/2? Yes, a negative 1/2 is one of the two possible values for m sub S, and it does not depend on the previous 3 values. So it looks like everything is good here. So we would circle D. D is a valid set of quantum numbers for an electron. Now the next 3 problems are a little bit more conceptual, so you might have struggled with them a little bit more. So let's take a look at them. Sample problem D, how many total electrons are in a filled 2p subshell? Well, let's figure out what this means. We know that a filled 2p subshell means that it has the maximum number of electrons in all of the orbitals in that subshell. We know that there are 2 electrons in each orbital. So we've got to figure out how many orbitals are in that subshell. Well, what does 2p signify? The first number is the n value, n equals 2. And the p designator means that the L value equals 1. Remember, S is the designator for L equals 0. P is the designator for L equals 1. So how many possible orbitals can we have? Well, the number of possible orbitals is equal to the number of possible m sub L values. So what are the m sub L values that I can have? If L is 1, then the m sub L values can be a negative 1, a 0, and a plus 1. So that tells me I'm going to have 3 orbitals in that subshell. So in the 2p subshell, I have 3 possible orbitals. And where have we seen that before? Remember, if we have p orbitals, we're going to have 3 of them, because there are 3 m sub L values that talk about their orientation. So there are 3 orbitals if it's a p subshell. If there are 3 orbitals in the subshell, and each orbital can hold 2 electrons, then we're going to have 6 electrons in a fully filled p subshell. And that's going to be true regardless of what the n value is. If the L value is 1, and that is a p subshell, it doesn't matter if it's the 2p subshell or the 3p subshell or the 4p subshell, there are going to be 3 of those p orbitals in that subshell. 3 orbitals times 2 electrons each equals 6 electrons total to fully fill up that p subshell. And in this case, the n value giving you that 2 number, totally unnecessary, because it doesn't matter what the energy level is. The number of orbitals is going to be dictated by whatever the L value is going to be. If it's an S subshell, there's only going to be 1 orbital in the subshell. If it's a p subshell, there are going to be 3 orbitals. If it's a d subshell, there are going to be 5 orbitals. Remember, if it's a d subshell, that d corresponds to L equals 2. So the m sub L values could be -2, -1, 0, +1, +2. If it's an F subshell, that corresponds to L equals 3, and that means that the possible m sub L values are -3, -2, -1, 0, +1, +2, and +3. So there's 7 orbitals in an F subshell. How many electrons would it take to fill up an F subshell? 7 orbitals times 2 electrons, it would require 14 electrons to fill up an F subshell. It would take 10 electrons to fill up a D subshell, 6 electrons to fill up a P subshell, and only 2 electrons to fully fill an S subshell, regardless of the energy level. All right, back to our sample problem. Sample problem E. Why is quantum number n equals 0 impossible? So if we think about that for a moment, n equals 0, the n value represents the energy level. If we had a 0 energy level, it would mean theoretically that the orbital and the electrons in it had 0 energy. So you can see why that's impossible, right? You can't have an electron with no energy. So it's impossible to have an orbital with 0 energy. And all of the other consequences of having n equals 0, you would have a size of orbital that was 0. The electron would spend 0 distance from the nucleus, and so forth. And moving on to our last sample problem, F. Why is there only one possible m sub L quantum number for L equals 0? Well, we know that the rule for m sub L is that it can go down to, m sub L can go down to -L up to 0 and then up to a positive L. So mathematically, I could just provide the rule, and that would say why there's only one possible value, because if L is 0, then the m sub L value must only be 0, right? But I'd like for us to think about this a little deeper. What is the physical reality of why there is only one possible m sub L quantum number? Well, remember that the m sub L quantum number refers to the orientation of the orbital in space. If the L value is 0, that is an s orbital. And s orbitals are spheres. So how many ways can you orient a sphere in space? Well, there are an infinite number of ways that you can orient a sphere in space. You can turn it all around. But regardless of which way you point it, they're all equivalent. So there's only one value that you're going to get, one equivalent value for that magnetic quantum number. Because regardless of which way you turn that orbital, it's always going to have an identical orientation. So the physical reality is that for s orbitals, because they're spheres, there's only one possible energetic value for that. And that's why there's only one possible value for its orientation in space. All right, so now we have covered the four quantum numbers, n, l, m sub l, and m sub s, what they represent, and their possible values. And we've extended on to talking about possible valid sets of quantum numbers and some of the conceptual significance of these quantum numbers as well. In our next video, we're going to use these quantum numbers to start developing a diagram that shows the priority in which electrons will start to fill orbitals.